Yeah. Good evening, everyone. Can somebody confirm? Like, are you able to hear me? Yeah. Yeah. Thank you. Actually, there is some bandwidth issue. That's why I'm not turning on my video. So please, and also there you may get some background noise. So please excuse me for that. Yeah. So good evening, everyone. I'm Shankar Rao, a PhD scholar from IIT Hyderabad. So today we are going to solve some previous year GATE ECE questions, mostly from signals and systems. And in this session, we'll try to solve 5 problems that are from convolution and Fourier transform and applications of Fourier transform for sampling. So, so just before that, just I want to ask one thing. Like, have you guys done with this Fourier transform sampling? These things I think you have studied, right? Continuous time Fourier transform and discrete time Fourier transform. Can somebody yes? Yeah, fine. So Chandrasekhar's questions in this only we will study about signals and systems. That too mostly from Fourier transform in this session. Discrete time Fourier transform and continuous time Fourier transform and its applications. Fine. So I assume that you guys have studied. So I'll start with. So if you have any questions in between, you can feel free to stop me and ask. So this is the question. This was given in GATE 2015 ECE in set 1 for 1 mark. So the result of the convolution, something is given. So we need to find out the convolution of this. So actually, so generally when we use convolution, let us say you have one system. Let us say you have one system and you are giving an input a signal x of t and h of t a system. The signal is passing through the system. Then let us say y of t is the output. Then the y of t is given by the convolution of the input signal and the system, right? Right. So this is where we use the convolution. Yeah, Karthik Bharatwaj. So you have raised hand. Can you ask? Hello. Fine. So so what is the let us say x of t and h of t. So how it is defined? Convolution. Can somebody tell me? X of t convolved with h of t is what? So integral minus infinity to plus infinity. X of tau h of t minus tau d tau. So this is the convolution, right? So and what about impulse signal? How an impulse signal looks like? So this is an impulse signal, right? So x-axis t, then this is impulse signal. So at 0 it is having non-zero value, and all other values it is having 0 value. That means del of tau is equal to uh, del of tau is equal to 1 when t equal to 0, and it is 0 otherwise elsewhere. Okay, this is impulse response. So in conventional way we will try to solve this. So here it is asked x of minus tau convolved with del of minus t plus t naught. So yeah. So x of minus tau convolved with del of minus t plus, sorry, minus t minus t naught. But we know del is an even function, right? So we know del is an even function. So del of minus tau, del is an even function. So del of minus tau is equal to del of tau. So we know del is an even function. So this we can write, yeah, this we can write del of minus, we can take common t plus t naught. So this, because del is an even function, this is equal to del of t plus t naught. So the given problem is now x of minus tau convolved with del of t plus t naught. But what is the convolution definition? We know by definition first we'll see, then we'll see some using some property. So minus infinity to infinity x of tau h of t minus tau d tau. So in this, now this I'll write here, minus infinity to infinity x of minus tau and del of t minus tau. Instead of t we have to replace tau. So t minus tau plus t naught delta tau is the convolution, right? Is this okay? First one is x of tau, but here we have t is the x of minus t. So in place of t here we have to replace tau. So x of minus tau into del of, instead of this t we have to place t minus tau plus t naught d tau. Now already we know, so when this equal to 1, the del of t we know only when the inside quantity del of t equal to 1, only that inside quantity is 0, otherwise it is this, right? So del of t minus tau plus t naught, when it is 1, it is 1 only when this inside quantity is 0. That implies what? When tau is, that means the inside quantity 0 means t minus tau plus t naught. When this is 0, that means when tau is t plus t naught, right? So already we have seen del of t how it looks like. So del of t is 1 only when the inside quantity is 0. Sorry, inside quantity is 0, yes. So otherwise it is 0. So here what we have, this del of, this one, del of t minus tau plus t naught, that means t minus tau plus t naught equal to 0. When this is 0, then del of t is 1. So here what condition we'll get if we equate to 0? When tau is t plus t naught, then only we will have non-zero quantity del of tau, that is 1. So in this integral, when tau is t plus t naught, then this will become 1, right? This will become 1. Now only when tau is t plus t naught, x of t exists, right? So from this, its value becomes x of minus tau when tau is t plus t naught into del of that one, that is 1. So its value is x of minus, when tau equal to t plus t naught, minus t naught. This is the option. So is this okay? So from this, yeah, D is the option, x of t minus t naught. Is this okay? Any doubts from this? Yeah, the question. The result of the convolution x of minus t convolved with del of minus t minus t naught. So this is traditional way of conventional way of solving that question, where we use the definition, that is convolution definition is my integral minus infinity to infinity x of tau h of t minus 2 d tau. So we are just substituting and simplifying. This we can also solve by using the convolution property of impulse. This we can solve. Fine. So in another way, like instead of doing all this, just we will use one property and we'll solve it. So we know x of t convolved with del of t minus t naught or anything. X of t convolved with del of t minus t naught equal to x of t minus t naught. Whatever we have solved, that only. This is the very standard property. This is called convolution property of impulse response. X of t convolved with del of t minus t naught. So this will come here. That's it. Is the convolution property of the impulse. With this, we can directly solve this. So the given question is x of minus t convolved with del of minus t minus t naught. So since del is an even function, this I can write like del of minus of t plus t naught, minus m taking common. Since it is an even function, so this is equal to del of t plus t naught. Now the question becomes x of minus t convolved with del of t plus t naught. So instead of t, this will go using this property, using this convolution property. So what you get is x of minus of, instead of t, you replace the t plus t naught. So that is x of minus t minus t naught. The same option will. So two properties we need to use here. One is the impulse is even function. So another thing is convolution property of impulse. With this we can solve this problem. Yeah. Uh, Jogeshwar Reddy, yes, he was telling actually we can solve directly by convolution property. Yes. Any? Do you have any questions or doubts from this? Tripartite questions are when we time shift an even function by uh, some tau, does it still remain even? Um, it will not actually. When we time shift it, and then it will not remain. Uh, Let us say we have one signal like this. So this is symmetrical about our vertical axis. So it is an even signal. Then let us say shifting this some amount of time I'm shifting, let us say right shift. Now this is no longer even, right? This is not symmetrical about vertical axis. All right. Just some time shifting, some right shift. Let us say if it is x of t, then I'm taking x of t minus t naught. Now it will no longer an even function. Okay. So similarly, just let us say impulse. Let us say del of t is this at 0. Now del of t minus tau, let us say is 0. Somewhere here it is shifted to tau. Now this is no longer even function, right? Did we take shifted impulse as even? Um, Actually, here if you see, uh, both look same. Let us say del of minus t minus t naught and del of t plus t naught. Actually, the both signals are same. This is del of t plus t naught is, if it is 0 here, somewhere at minus t naught, we have an impulse, right? And this one, if you do this, minus of t plus t naught. First you do mm, there is some confusion. This one, yeah, this is both are same actually. See, this is one, sorry, this is equal to 1 when t plus t naught equal to 0. That means when t equal to minus t naught, its value is 1. Similarly, in this case also, this is equal to 1 when minus t naught equal to 0. In this case also, minus take common, t plus t naught equal to 0. That means when t is minus t naught. In both the cases, in the both the signals, when t equal to minus t naught, its value is 1, and in remaining all other cases, it is 0. So both signals are identically equal, but in general, impulse function is an even function. But here, I think we should not say then. I'm taking back my word. Shifted version of impulse response need not be an even function. It is even with respect to that time shift, with respect to the t naught. Let us say it is shifted by t naught. It is even with respect to that time instant t naught, but not with respect to origin. Okay. But this property, what property we can use? Del of minus t equal to del of t. Is that okay? Yeah. So actually, the impulse is even when there is no time shift. When it is there is a time shift, it is even with respect to that T naught. But okay, but here that that we can understand that property del of minus t equal to del of t. Okay, in this way I'm telling we need to use two properties, del of minus tau equal to del of tau and convolution property of impulse. Yeah, fine. Uh, Let us move to the next question. Yeah. Can some this is the question you can read out, and can somebody give me a hint how we can do it? This was given in GATE 2016 ECE, set to for 10 marks. So sorry, for 1 mark. So can somebody unmute and tell me how we can calculate the energy of a signal? Okay, by using direct formula. So let us say energy of x of t is what? Minus infinity to infinity x of t whole square into dt, right? Yeah, rect function, yes. Herschel's one, yeah, rect function. Actually, solving this is quite difficult if you directly use in solve in time domain. So this is the energy of any signal. Uh, let us say if it is an energy signal, provided if it is an energy signal, this is the energy of the signal. But it is difficult to solve, right? Here we have sinc function, right? Sinc 40, that's the function given is some kind of sinc function, but it is very difficult to integrate. We can solve it, but difficult to integrate. Now we will here we will take the help of one of the property of Fourier transform, that is can somebody tell me Parseval's energy theorem, right? Parseval's energy or theorem. It states that let us say a signal is there. Let us say a signal x of t is there, and its Fourier transform is x of omega. Okay, this is the time domain x of t, and in frequency domain x of omega. Then energy of the signal in the time domain is equal to the energy of the signal in the frequency domain. That tells that is the Parseval's theorem. So energy of the signal in time domain equal to, that is minus infinity to infinity, minus infinity to infinity x of t, x of t whole square dt equal to the 1 by 2 pi minus infinity to infinity x of omega square d omega. Okay, so minus infinity to infinity x of t whole square dt equal to 1 by 2 pi minus infinity infinity x of omega square d omega. X of omega is the Fourier transform, and this quantity is called energy spectral density or power spectral density. If it is an energy signal, then it is called energy spectral density, that mod x of omega square. If it is a power signal, that is called power spectral density. Here why I am taking modulus means if it is a complex signal, instead of square, let us say x of t into x of its complex conjugate, so you will get a mod. That's why I'm just writing mod. So if we for this problem, if we use this Parseval's theorem, if we calculate the energy in the frequency domain, then it is easy. So for sync, I think you know it. I'm not going to derive here. It is very standard one. Suppose you have sync function something like this, sin at by pi t. This is the time domain. In the time domain, if it is a signal, its Fourier transform is a rectangular pulse. Its Fourier transform is a rectangular pulse. In omega domain only I'm writing. So its width is 2a. Its width is 2a, and amplitude is constant, that is 1. Okay, hope you know this property, right? So actually how we derive this is I think you know this. If you have a rectangular pulse in time domain, let us say if you have a rectangular pulse minus t by 2 to t by 2, this will say a rect t by t, right? A rect t by t. Its Fourier transform is, it's a very standard one. For competitive exams and all, we have to remember this. At the omega t by 2. It is sa omega t by 2. Please correct me if I'm wrong. So sa is sin x by x. Sinc is sin pi x by pi x. Sa is sin x by x. So 8 is sa omega t by 2. This is the Fourier transform. And if you use duality property, I think you know the duality property. If we use the duality property, then from this we can derive this one. Okay. So sin at by pi t, whose Fourier transform is this one. Now, is that okay? So now the given question is sin 4 pi t by 4 pi t. So the given question is sin 4 pi t by 4 pi t. So it is like the a is what? 4 pi is a, and we can just take this 1 by 4 common. So 1 by 4 if we take outside, then we will get sin at by pi t form, right? So its Fourier transform is in omega domain. A is 4 pi, right? So minus 4 pi to 4 pi, and 1 by 4 is the amplitude, because 1 by 4 we took common. 1 by 4 the amplitude. Now energy in the frequency domain is already we know. So 1 by 2 pi, okay, integral minus infinity to infinity x of omega square. So here integration limits are from minus 4 pi to 4 pi, because the rest the value of the signal is 0, right? So 1 by 4 square d omega. So this what we'll get after integrating 2 pi 1 by 2 pi into 1 by 16 into d omega. So 4 pi minus 4 minus of minus 4 8 pi. So what we get is 1 by 4 we get, right? 1 by 4.25. So is that okay? Any doubts from this? Yeah. See, actually, so here, just a recap once again. So energy, they are asked the time domain signal, it is given, but the integration is somewhat difficult doing that integration. So we use the Parseval's energy theorem or power theorem. That is, energy of the signal in time domain equal to energy of the signal in the frequency domain. The energy will not change. So for the given signal, just we are calculating we are finding out the Fourier transform, that is using the standard property sin at by pi t. If you have the signal, then its Fourier transform is this one, a rectangular function in the frequency domain. Now that can be easily integrated. So after solving it, we got 0.25. Any doubts? Can we move to the next question? Yeah, thank you. So the next question is, That is the question. It was given in GATE 2017 ECE set 1 for 2 marks. So let me read out the question. Let h of n be the impulse response of a discrete time linear time invariant filter. So the impulse response is given by h of 0, h of 1 and h of 2 is given. In rest of the places it is 0. If h of omega be the discrete time Fourier transform of h of n, where omega is the angular frequency, and given that h of omega naught is 0, then what is the value of omega naught? It's a straightforward question. So here what they're giving is they have given is the discrete a system, an LTI system, LTI filter. The impulse response is given. Okay, here since it is a discrete signal, that's why we use discrete time Fourier transform. Anyway, the discrete time Fourier transform h of omega is given. We need to find out the discrete time Fourier transform and h of omega, and we have to equate to 0 to find omega naught. H of omega will find out, and we will equate it to 0 to find omega naught. Can somebody just tell me what is the discrete time Fourier transform? The formula for that. Okay, let me draw first the impulse response. It is given impulse response at 0, 1 and 2. Its value is 1 by 3. Okay, and at the other places its value is 0. Its value is 0. Okay, this is h of n given. Fine. Now since it is a discrete one, it is a discrete one. So if x of n is a discrete signal, then the discrete time Fourier transform of that dtft of x of n is, that will say x of e power j omega. We will represent like this. A continuous time Fourier transform, we will say x of omega, and discrete time Fourier transform, we will say x of e power j omega. And some textbooks they may represent this also, x of omega. So this is equal to sigma n equal to minus infinity to plus infinity x of n, okay, e power minus j omega n, and this is the discrete time Fourier transform. So from the problem we need to find out Fourier transform, then we have to equate it to 0. Fine. Now h of omega is what? Let us say h of omega. So only we have h value at only at 3 values, n equal to 0, n equal to 1 and n equal to 2. H is having some finite value 1 by 3, and at the rest for remaining values of n it is 0. That's why we can take only those 3. So h of 0 into e power minus j omega 0 plus h of 1 into e power minus j omega 1 plus h of 2 into e power minus j omega 2, and remaining places h of 2, h of 3, h of minus 1, h of infinity, everything is 0. That's why just the rest becomes 0. Since 1 by 3 everywhere, h of 0, h of 1, h of 2, everything is 1 by 3. So 1 by 3 I'm taking common. All values are 1 by 3. 1 by 3 into first one is 1. Omega 0, e power 0 is 1 plus e power minus j omega plus e power minus j2 omega. Just I'm taking e power minus j omega common I'm taking. So what we get is 1 plus e power j omega plus j omega plus e power minus j omega will get. Okay, this is h of omega. So what we want is at what value of omega naught, at what value of omega we will get 0. This h of omega becomes 0. We need to find out omega naught. We need to find out omega naught such that h of omega naught equal to 0. So yeah, let me replace omega instead of omega naught 1 by 3 e power minus j omega naught into 1 plus e power j omega naught plus e power minus j omega naught equal to 0. We need to find out to solve this equation. We need to find out omega naught. So if you see this cannot be 0. The first term, this one, which one I circled, this cannot be 0 because 1 by 3 is a constant e power something. It is 0 only when omega naught is infinity. But we know for discrete time Fourier transform, omega naught limits we know minus pi less than or equal to omega less than or equal to plus pi. We know the discrete time Fourier transform, it's a periodic. In the frequency domain, it is a periodic signal. So this can't be 0. The only option is the second term should be 0. We need to equate the second term to 0. Now, if you see that e power j omega naught plus e power minus j omega naught is 2 cos omega naught, because we know uh, cos theta is what? E power j theta plus e power minus j theta by 2. This we know. This we can express in terms of exponential. So in the similar way, so that property we can use here, that formula. So 1 plus 2 cos omega naught equal to 0. Okay, first term cannot be 0, the second term only 0. We need to make equal to 0. So here, so omega naught is what? Cos omega naught is minus 1 by 2. So omega naught is cos inverse of minus 1 by 2. So when omega cos, at what value of omega naught, it is 1 minus 1 by 2. Now cos is negative in the second quadrant. When it is 120 degrees, then it is minus 1 by 2. Cos 120 is minus 1 by 2. So omega naught is what? 120 means in radians. Sorry. Omega naught equal to 2 pi by 3. So it is a fill in the blanks kind of question. So 2 pi by 3 around you'll get 2 by 3 into 3.14. We'll get, it got stuck. Just give me a second. Yeah, it is something like 2.09 we'll get in radians, 2.09 radians. So in the question, it is asked fill in the blank type question, right? 2.09 around, but they'll give some error. So in the gate, if it is a fill in the blank kind of question, up to some deviation they'll allow, maybe from 2.05 to 2.10. Somewhere here, if you write anything in between them, it will take as correct. Is it clear? Yeah, fine. If you have any doubts, you can ask me, or else we can go to the next topic, I mean next set of questions. So in the question, they have given a impulse response of an LTI system, discrete time LTI system, and they are asking like for what value of omega naught the impulse response, the h of omega naught will become 0, the transfer function. So we need to find out dt of t, then make it equal to 0. Fine. Let us go to the next question. This is Fourier series 1. Maybe next class I'll take Fourier series 1. You know, but now I'll go to one of the application of this uh, Fourier transform, that is sampling. So this will solve now. This question was given in GATE 2018 in ECE for 2 marks. The question is, a band limited low pass signal x of t of bandwidth 5 kHz is sampled at a sampling frequency fs. Okay, the signal x of t is reconstructed using a reconstruction filter h of f whose magnitude response is given below. So the minimum sampling rate required for perfect reconstruction of the signal is. Uh, can somebody give me a hint like how we can solve this? How to solve this problem? Am I audible, right? Yeah, thank you. Can somebody tell me how to solve this? This question is regarding sampling. So, and also we need to use the Fourier transform. So the question what is given in this question is, you have a signal x of t. You have a signal x of t. It is passed through a sampling circuit, sampler, let us say. Okay, it is passed through a sampler. Then we will get the sampled version of signal. Okay, x del of t. You know, right, what is sampling? At uh, regular intervals of time, we will take samples from the signal. Instead of transmit, let us say, transmitting or using the entire signal, we use the discrete values of the signals. That is sample signal. Now, they are asking in the question, for perfect reconstruction, it is a sample signal is there. Again, we have to reconstruct the original signal from that. So it should be passed through a reconstruction filter, some kind of low pass filter that you know, I guess. So a sampled version of signal, when this passed through a reconstruction filter. So reconstruction filter, then we can retrieve the signal. So x of t, let us say x of t. Maybe there may be some scaling, some amplitude scaling will be there with some factor k, but uh, other than that, we will be able to retrieve signal as it is. So generally we use some kind of reconstruction filter, low pass filter for reconstructing this. Now, so this filter response, it is given in the question. See, the filter reconstruction response, the response of the reconstruction filter is given, the frequency response. This is the response. Now for perfect reconstruction, so what is the value of minimum sampling rate fs? What is the minimum sampling rate for this? Okay, I think you might have had like a Nyquist rate. Suppose a signal should be sampled with the minimum Nyquist rate so that you can reconstruct the signal, original signal. So if it is fs greater than or equal to 2 fm, uh, right, that you know. So but here the filter response also given, what will be the minimum, that one we need to see. Is that okay? So here the signal x of t is given. X of t is band limited to 5 kilohertz. That means x of t, let us say the signal in time domain, its Fourier transform is x of omega, let us say. it is having this kind of response. We don't know exactly how it looks like, but it is band limited to 5 kilohertz, they said. Let us say omega. So 5 kilohertz, f is 5 kilohertz, so omega is 2 pi into 5 kilohertz. Is that okay? No, the signal is given, it is band limited to that omega m. Let us see. That means the signal is having frequencies below omega m. The signal will not have any frequencies above omega m. Okay, that is a band limited signal. Okay, is that question clear? Then we can, yeah. So okay, right, the signal is passed through a sampler. The sampler is having some sampling frequency fs. Okay, then we'll get the sampled version of signal, then it will be passed through a reconstruction filter without any aliasing. We'll say without any distortion we should reconstruct it, recover it. For that, what should be the sampling frequency? So that is asked. So I think we are somewhat running out of time. Let me project already solved one. I'll just projecting here. I'll just explain that one. I thought like if there is some bandwidth problem, if while writing, if there is a delay, I thought I can show this one. Beforehand I solved it. Yeah. Yeah. First, let me, can you see, change the screen? Yeah. We will first see the sampling concept, then we will solve this. Okay. Sampling, you know, right? How we'll get a sampled version of signal? Let us say x of t is the signal here. So let us say x of t is the signal here, this one, x of t. I think there is a delay. Yeah, x of t is the signal here. Now to get the sampled version of signal, it's like mathematically equivalent to multiplying the signal in the time domain with the periodic impulses. Okay, na? Now x of t is multiplied with periodic impulses. You can see here this impulse train, we will say impulse train. The impulses are placed at an interval of ts. Okay, at 0, ts, 2 ts, minus ts, minus 2 ts. So this is periodic impulse train. This is expressed like this, right? Sigma n equal to minus infinity t plus infinity del of t minus nts, right? When n equal to 0, at del of t it will have value. When n equal to 1, then del of t minus ts, right? At ts it is having value like that. So this is the impulse train. When x of t is multiplied with impulse train, then we will get the sampled version of the signal. This one you can see, this is the sampled version of the signal. That means at those particular time intervals we will just take the values, we will sample the values. Okay, let us say x of t, this is x of t, the sample signal is x del of t. Now here the sampling frequency means how the impulses are placed. Based on that only the samples will take, right? From the signal here we will take the samples, right? Here this is one sample, this is one sample, this is one sample, this is one sample, like this, right? This we are discretizing the signal, right? So let us say ts is the spacing between the samples, time period. So ts is 1 by fs, that's the frequency. And other words we can express omega s, the sampling frequency in radians, 2 pi fs or 2 pi by ts. So how we can express the sample signal? X delta of t, this one, x del of t equal to x of t multiplied by train of impulses, x of t into sigma n equal to minus infinity to plus infinity, sigma n equal to minus infinity to plus infinity del of t minus nts, t minus nts. Okay, this is the sample signal. No, actually we'll try to understand this. Actually the question is they are asking in the frequency domain, for what value of fs sampling frequency reconstruction is possible without any distortion, like that it is asked right in the question. And also for the reconstruction filter they have given the frequency response. If you see the magnitude response they have given, So if you solve this, if you analyze this question in the frequency domain, then we can easily get the answer, or we can have the clear picture of what's going on. Okay. Now this is x del of t is the so x del of t is the sampled version of signal. Now for this Fourier transform I'm taking. So frequency domain, if you want to analyze, means Fourier transform we have to take. So Fourier transform of x del of t is this one, x del of omega, capital X del of omega is the notation. So actually I'm not going to explain this here. So actually this is a periodic signal, right? If you see, generally for periodic signals we calculate the Fourier series, right? I think you know this. If it is a periodic signal, then we will calculate Fourier series. If it is a non-periodic signal in time domain, then we will find out the Fourier transform. But also for periodic signals, also this kind of periodic signals, we can find out the Fourier transform. Okay, so the Fourier transform of this is this one. So how to find out the Fourier transform? If you see here, you can assume this as two signals. X of t is one signal and another signal is sigma del of t minus nt. Is two signals are there. So in time domain multiplication, frequency domain convolution. I think you know this, right? In the time domain it is multiplication. In the frequency domain it is convolution. So in the Fourier transform, just I'm writing here. The Fourier transform of x of t is x of omega 1 by 2 pi into x of omega convolved with 2 pi by ts 2 pi by this is the Fourier transform of this impulse train. Okay, the Fourier transform of impulse train. I think there is a delay here. Yeah, due to internet issue there is a delay. So this is the Fourier transform of impulse train, sigma n equal to minus infinity to infinity del of t minus nts. This is the Fourier transform, 2 pi by ts sigma del of omega minus n omega s. Here omega s is nothing but the sampling frequency, 2 pi fs. Okay na? Now this is the using the convolution property of the impulse. Now you can cancel this 2 pi and 2 pi, you can cancel. Now we know already the convolution property of impulse we have seen. Something like x of omega convolved with del of omega minus omega naught is x of omega minus omega naught. So this will get 1 by ts into sigma n equal to minus infinity to plus infinity, this one. This is the Fourier transform of the sampled version of the signal. Is this clear till here? Okay. See, actually this is the sampled signal. This is the sample signal x of t into something impulse train. So this we can assume as two signals x of t into some y of t. So if you take the Fourier transform in the frequency domain, it is 1 by 2 pi into Fourier transform of x of t, that x of omega convolved with y of omega. So 1 by 2 pi into x of t, let us say Fourier transform x of omega. For impulse train, this is the Fourier transform. Then we need to use the convolution property of impulse response. Then we'll get this one. So this is the Fourier transform of the ideally sampled signal. If x of t is the signal and its sample signal is x del of t, then its Fourier transform is this one, 1 by ts into sigma n equal to minus infinity infinity, this one. Now this, how we can represent this? Let us say x of omega is this one. Already we know it is given x of t is a band limited signal 5 kilohertz. So x of omega is this one. Let us say Fourier transform of x of omega is this one. Then what? This is a periodic signal, right? This one is a periodic signal, right? It is a train of the x of omega will be repeated again and again. Shifted version will be repeated again and again. So when n equal to 0, if you replace here sigma n equal to minus infinity to plus infinity is there. So when n equal to 0, if we place, it is x of omega, this one, green one you can see. When n equal to 1, I replace x of omega minus omega s. So shifted version, right shift. And when x equal to minus 1, so left shift. Like this we'll get periodic, x repeated periodically. Okay, x repeated periodically. This is the signal. Okay, now we have this one. This is the Fourier transform of the sampled signal. Okay, x del of t, x del of t is the sampled signal in time domain, x del of omega is the Fourier transform in the frequency domain. So you can see here the Fourier transform of the signal in the frequency domain, this one, sampled signal. And this x of omega repeated again and again, x of omega repeated again and again periodically. Now, so I think from this we can derive the Nyquist criteria. This is not required for this, but just in the context I'm just explaining this. If you see here, suppose if you want to use some kind of a low pass filter, if you want to reconstruct only this, let us say this is the low pass filter. You can see this is the impulse, frequency response of the low pass filter, this kind of one. So if this signal is passed through a reconstruction filter, then only the signal, the filter will allow only this signal, and it will reject all other signals. Okay, then only we can reconstruct the signal. Now for that to happen, what is the condition here? If you see the samples, the samples are closed very near, let us say the sampling frequency is very less, then the if this this x of omega, the shifted versions of x of omega are closely placed, then what will happen? There is a overlap here, right? There is a overlap. So if we use a reconstruction filter here, what will happen? Here at the edges where there is a overlap, uh, what there we will get some distortion, because only x of omega we cannot get from this. X of omega plus this overlapped portions will be there. So that's why we will have some distortion. This is called aliasing. So for that, to avoid aliasing, what is the condition here? There should not be any overlap. Here you can see there should not be any overlap. So omega s, let us say this is omega s. See here, just I'm writing it here again. Sorry, this is 0 and this is omega s. This is 2 omega s. This is minus omega s. So since its bandwidth is omega m, so this is what omega s minus omega m, and this is what omega m. There should not be any overlap, means what? The lower edge of the second signal, this one, should not touch the upper edge of the first signal. That means omega s minus omega m greater than or equal to omega m. So that is the condition to avoid aliasing. Okay, so this one, the lower edge of the second one should be greater than the upper edge of this one, that is omega s minus omega m, this one, omega s minus omega m greater than or equal to omega m. So from here omega s greater than 2 omega m, in f domain fs greater than 2 fm. So this is called this is the minimum frequency required for avoid aliasing, right? This is called Nyquist criterion, right? If the maximum signal frequency is omega m or fm, so in this, so x of omega is given, this is the maximum signal frequency, right? Then to avoid aliasing, the sampling frequency should be at least 2 times the maximum signal frequency, that is omega s greater than or equal to 2 omega m, or fs greater than or equal to 2 fm. This is the Nyquist rate. Okay. Now while coming to this question, let us understand this question. Now this is the signal, this is the Fourier transform of the signal. Okay, this is given. Now reconstruction filter also given. Now we have to find out the frequency, sampling frequency, such that the we should be able to successfully reconstruct the signal. So this is already explained. So here the sampled version of the signal is passing to the reconstruction filter, then we will get the reconstructed version of the signal. So x del of omega is the Fourier transform of the frequency domain representation of the sampled signal. This is passed through the reconstruction filter. Okay, a reconstruction filter, what they have given, this one they have given, right, h of omega. Let me go to the question. So yeah, got stuck, sorry. So this is the question, right? Yeah, this is the question. Already they have given. Now we need to find out the for what sampling frequency we can successfully reconstruct the signal. Yeah, you can see here. Now x of omega is passing through this filter. This we have to multiply with 2 pi because it is given in frequency domain. Now if we can see here, this the signal should be within the frequency domain representation of this. That means this x of omega should be within this filter. It should be within this filter. And the next one, x of omega minus omega s and x of omega minus omega s should be outside of the filter. Okay, x of omega minus omega s and x of sorry, minus omega s, sorry, omega s, these two should be outside of the filter. Then only we will get only x of omega, will get, all other can be avoided. That is when it is possible. It is possible when omega s minus omega m, this one is omega s minus omega m, when omega s minus omega m is greater than this one, greater than or equal to this one, 8k. This is 8k, it is given, right? Filter upper edge is 8k, this is given, right? So in omega domain 2 pi into 8k. So this one omega s minus omega m greater than or equal to 2 pi into 8k. In that case only we can avoid the aliasing. Only the first harmonic only we can capture. The rest of the harmonics we can avoid. So omega is 2 pi fs, right? So the 2 pi I'm just eliminating. So fs minus fm greater than or equal to 8k. But fm already given, right, in the question. The signal is band limited to 5 kilohertz. So fs greater than or equal to fm plus 8k. So fm is 5 kilohertz already given. So 5k plus 8k 13 kilohertz. So fs greater than or equal to 13 kilohertz. So the question it is asked, what is the minimum frequency? So minimum frequency is 13 kilohertz. Is that okay? Is that okay? 13 kilohertz is the minimum frequency. Yeah. Anyway, these things, this will be posted in the NPTEL website. The video solutions will be posted there. Yeah. You can see here fs greater than or equal to 13 kilohertz. So the minimum frequency is 13 kilohertz. The answer is 13 kilohertz. Yeah. Thank you. Thank you all. Yeah. Thank you all.
Yeah, thank you. Yeah, thank you. Yeah, thank you. Yeah, thank you.
You can join the next session. Yeah.